electrolysis reactions. That's how you can put molecules together, take them apart, like in digesting or in building structures. And then we went on and talked a little bit about lipids and said there's saturated fats and oils, which means they have all single carbon-to-carbon bonds. Then there's unsaturated. Unsaturated puts a bend in the long carbon chain and makes that molecule liquid at room temperature. So I told you at the end of the 1950s, there was a lot of oil left over from World War II. And so they took this oil and they used it and hydrogenated it in order to make margarine and Crisco. So the benefits of it is that it's a softer type of fat compared to butter. So it's easier to spread. It doesn't get as hard even when it's cold. It has a much longer shelf life and it's cheaper. So those were all positive things. And so they like went on this big thing saying that it was healthier. It was really sort of like pushing it. It's healthier since it's not an animal product, because animal products like butter contain cholesterol. So margarine and Crisco are cholesterol free because they're actually a plant product because they're an oil type. So if you look at what happens in that reaction, when we think of complete hydrogenation, that would be taking the double bond in the long carbon chain that is a cis arrangement. Remember, cis means like the bonds angle at the same direction. Taking it and breaking the double bond so that it becomes a saturated chain, meaning all singles. So can you see when you look along this, you can see that this is all single carbon-to-carbon bonds. You remove or break that double bond. By making it saturated, remember those are like knives in the drawer. Those like can pack in nice and tight. And this allows this to become solid at room temperature. But in truth, the way that they do hydrogenation is they don't do complete hydrogenation. So yes, 99% ends up being completely hydrogenated and going from that cis double bond to being solid at room temperature as margarine, but there is a small amount of reactions where instead of breaking the double bond kind of like opens and then it reforms. And when it reforms, it forms a double bond that doesn't have that cis conformation, but instead, remember we said cis and trans? Cis means on the same side. So with cis, the natural arrangement of double bonds in oils in nature, they're always in that projecting upward. But notice the trans. So the trans double bond creates a bond that still takes, the molecule still takes that zigzag appearance. The only problem with this is there is no naturally known enzyme that can break a trans double bond. So this bond is not digested. So if this molecule gets absorbed, so it gets mixed with bile and gets absorbed into your bloodstream, there is no way to break that trans bond. So then the question becomes, well, what happens to it? if it can't get digested because of its bond shape, and remember enzymes are very specific as to what kind of bonds they can break and can't. They started doing studies about it and said that these fats tend to build up, that they play a part in increasing your circulating triglycerides, increasing your LDL, which is your bad cholesterol, decreasing good cholesterol values, and that together plays a role in an increased risk of heart disease. So interestingly enough, it was about 2004, 2005 when Europe banned trans fats. The United States was a little bit behind the times. They had to think about it a little bit longer. And a lot of it has to do with the food manufacturers have very strong lobby with Congress. So they like keep pushing and going, no, we need more time, we need more time. Initially, it was supposed to be like 2010. Then it got pushed back to 2012. Then it got pushed back to 2015. So it was like all the time I was teaching this, I was like, well, it was supposed to be banned last year, but they got an extension. So food manufacturers said, we have to retool all of our recipes because if we can't use the same exact margarine or oil, if we have to go to a different form, then it's going to end up affecting these recipes and we have to redo them. But as of May 2019 in the United States, there are no trans fats in any type of packaged foods. So just looking at this, if it will let me. So looking, you saw it, didn't you? Arg. So if you're looking at, magnify slide. Nope, won't let me. All right, but if you're looking at this and you see, I know one way to do it. There's more than one way to fix this. Up, up, up. So looking at this image, what kinds of things do you routinely use, eat, etc.? When you look at this, what do you see? Right? So all those like convenience foods types of things. So there's cookies, the prepared cakes, you know, like the cakes that you could buy, the frozen cakes are already made. Then any of you use like the Pillsbury biscuits? Okay, the Pillsbury biscuits are in there. There's also like the cookie dough, microwave popcorn. So like the oil in microwave popcorn, frozen pizzas, even pie crust, like that's like one of those graham cracker pie crusts, and then frostings, like prepared, all the stuff that's like already made that you would then just like basically open and use. Okay, all of those things routinely had trans fats in them because of the type of fat that was used. Now those do not. Okay, so as of 2019, those were actually taken. They had to redo them. Some people said that cookies changed how they tasted. Some people because I remember teaching this in like 2017, 18. People were like, yeah, like Oreos don't taste like they used to. And part of it is they actually had to go and use a different type of fat or shortening in making their cookies. You can still use margarine, but the margarine that is produced now, when you look at margarine, even like Parquet, Blue Bonnet, Imperial, all the different kinds of margarines, they do not have trans fats in them anymore. So they had to change their production style so that they could have foods that would not have oils that were made with those trans fats. Unfortunately, the only place that I could find, because I was like, well, is there any trans fats? Trans fats, so if you start off with a solid fat, so like whether bacon grease or shortening, anything that is if you start off with anything that's a liquid, so that would be like canola oil, vegetable oil, any kind of oil, even peanut oil, that's going to have the double bond in it, because remember that makes it a liquid at room temperature. If that is heated for prolonged periods of time, heating can cause hydrogenation to occur. And so there are some molecules that can actually produce trans fats because they don't completely hydrogenate. So the double bond is in the cis. When you hydrogenate, you like break it, but then it just reforms, and it reforms in the trans arrangement. So when you think about oils that are heated for a long time, can you think of any instance where there is a food place where they have their fryers on all the time? Well, those are possibilities. I don't know if they leave them on overnight, but I always think of like what are places that are open 24 hours? Like McDonald's, like a lot of the fast food restaurants. So a lot of the fryers in fast food restaurants, they start with oil and it's on and it's hot all day long. And that heat can actually cause hydrogenation reactions to occur with the oil. Some of that oil then would become a solid when you cooled it, but some of it will form those trans fats. So that's the only place that I can find, and I'm like, great. So like donuts, French fries, fried chicken, that those are actually still sources of trans fats just because of the heating of the oil that takes place. There's only one other type of reaction where we're breaking a double bond. And in this example, we're doing what they call a hydration. So remember, hydrogenation is adding hydrogen. Hydration. What do you think of when you think of hydration? Yeah, I always think of water. Like if you're hydrating, you're trying to drink more water. So hydration is adding water to the double bond. So water is H and OH. So what happens is, remember that double bond is more reactive, so it's the one that splits. And so what ends up happening, a hydrogen gets added to one of the carbons, the alcohol group gets added to the other. So you're going to break the double bond and you're going to make an alcohol group. Oh. So we're breaking the double bond and you'll form an alcohol. So that's called hydration. So I've got a couple of ones to kind of practice and recognize. So remember, if you're thinking hydrogenation, we're going to add hydrogen to the double bond and it'll form a single bond. If you're thinking of hydration, this is you're going to add water to the double bond and it'll form an alcohol. So hydrogenation is adding hydrogen to the double bond. Hydration is adding water to the double bond. Hydrogenation just makes a saturated chain, all single bonds. Hydration is going to make one of those an alcohol. One of those carbons will end up having an OH attached to it, and that's an alcohol. So I do not expect you to finish the reaction. It's really more just identifying what the reaction is. So we have hydrogenation, hydration. Then remember that we have condensation. In condensation, we're going to join two molecules, and water is a product. Right? So that's where those two come together. H comes off of one, OH off of the other, makes water and links them together. The opposite reaction is that hydration reaction. And hydration is going to break one molecule into two. Break one molecule into two by using water. So water is a reactant. Then we had the combustion reaction. A combustion reaction is any kind of fuel plus oxygen making carbon dioxide and water. So looking at those five,
what did it say, hydration? What?
Hydration is when I break one molecule into two by using water. So water is a reactant in a hydrolysis, I should say hydrolysis, not hydration, sorry. I said hydrolysis and I wrote hydration. Huh? Did you write it wrong? Oh. I think I said hydrolysis and then I wrote hydration. Brain cramp. Right, so remember condensation and hydrolysis are like opposites.
So that's hydrolysis.
Mm-hmm. And then the last one is a combustion reaction. Remember that one was kind of different than synthesis or decomposition or a single or double displacement because it's whenever you take some kind of carbon fuel plus oxygen and you'll always make carbon dioxide and water as long as it's a complete combustion. So I would throw that in as another reaction example. So these are kind of like the five.
Is that combustion says what?
Yep. Combustion is if you take a fuel
Fuel.
plus oxygen and you make carbon dioxide and water.
Thank you.
So that's how you recognize it. So looking at these, you tell me, what is the first one? So look at those 5. It's what? Say it again.
Hydrogenation.
So if it was hydrogenation, because it says it's like the word hydrogen is in it, hydrogenation breaks the double bond by adding hydrogen. So this is breaking the double bond by adding water. So that makes this hydration. Okay. So remember that to remember this, you're going to break the double bond between the 2 carbons by adding water. And see, there's an alcohol that's formed. So what's the second one? Hydrogenation. Or hydrogenation. Right? Because that's adding hydrogen to the double bond. So see how the double bond on the left becomes a single bond? So the C to C, the carbon connection is a double bond, and then it becomes a single. So this is adding hydrogen to that double bond. Converting it to a single bond. Okay, so now look at the next one. So out of the 5 ones we talked about, what's this one?
Hydration.
No, not hydration. Hydration is breaking the double bond using water. I'm using water, but what am I doing? I'm not breaking a double bond. Condensation would be putting 2 things together and water as a product. Where's water in this reaction? It's on the left, so that means it's a reactant. Water is a reactant. It's hydrolysis. So this is hydrolysis. So ways you can tell hydrolysis, water is a reactant. And do you see that one big molecule? Do you see that this and this are the same? And this and this are the same. So what did I do? I took this molecule and I split it in half. So that's CH3, CH2O, and the C double bond O, CH3, those split. I added hydrogen to one side, alcohol group to the other side. So this is the water right here. The H and the OH. That's what split this molecule in half. That's why they call it hydrolysis. So like think of that as water is breaking. So in this, I started off with a bigger molecule. I used water to split it in half or to make it smaller. So in this, water is a reactant. And the larger reactant, in this case, that's CH3, CH2, C double bond O, CH3, the big molecule on the left becomes 2 smaller. So it forms 2 smaller products. So if you see that water is a reactant, look for the double bond. If there's a double bond, it's hydration. If there isn't a double bond, like that one, I didn't break the double bond. There's a double bond O, but it stays the same. It's still there, right? But if water is a reactant, it's going to be hydrolysis unless I'm breaking a double bond. So the one up at the top, the water is a reactant, but there's a double bond that's broken. That's how I know that's hydration. So that's how you can tell the first one and the third one apart, hydrolysis versus hydration. Both of them have water as a reactant. Hydration, I'm breaking the double bond. Hydrolysis, I'm actually splitting a molecule into two. So remember, this happens like in digestion. When you start with big molecules, you got to start chopping them into smaller molecules. It's water that ends up being added to the bonds to be able to break them in half. All right, what about the bottom one then? That means the bottom one is hydration. Do you see the difference? See how both of those include, do you see both of them have water as a reactant? This is hydration. Water is a reactant, just like the one above it. But the double bond becomes a single bond. So you see the double bond in the reactant is now a single bond, and that single bond always ends up having an alcohol attached, that OH. All right, so look at the top one. Tell me what this is.
What is it? Hydration?
No. What's on the reactant side? It's not water, it's hydrogenation. Okay? So how do you pick that one? So you notice that H2 is a reactant.
Where you see that at? Where y'all at? Oh.
Mm-hmm. Right? So H2 is a reactant, just hydrogen.
Oh, so we on the red joint?
The one at the very top?
Oh.
Mm-hmm. The very top, hydrogen is a reactant. And do you see that the double bond goes to a single bond? So when you look on the left, you see a double bond. When you look on the right, you see a single bond. So if it's that, you know it's either hydrogenation or hydration, whichever one gets added. If it's hydrogen added, it's hydrogenation. If it's water added, then it would be hydration. So it's really a matter of like sitting down, like looking at them. Okay, how do I recognize this? This one I would recognize, look at the double bond and then look at the hydrogen, right? So if there's a double bond and a hydrogen on the left, it's going to be hydrogenation. If there's a double bond and a water on the left, then it's going to be hydration, because those are both breaking a double bond and converting them to a single. Okay, so what about this one?
Which one?
The next one, the one in blue.
In blue?
Mm-hmm. This whole big thing.
Where is it?
All of this.
Oh, that's blue?
Mm-hmm. This whole thing. What is that?
Hydration. No?
Nope. Hydration would be breaking a double bond. I'm not breaking a double bond. Mm-hmm.
I get those two mixed up.
Yep, because those are both having water as a reactant. Mm-hmm. So the way to tell those apart, if you see a double bond being broken and water as a reactant, you know it's hydration. If you see water as a reactant, there is no double bond, which is why it's not hydration.
Oh, okay.
Okay, but do you see I left the water red, the H and the OH, so you can see where they go? Mm-hmm. So I broke the bond between those two rings by adding hydrogen to the oxygen and an alcohol group to the other side. So water is HOH. So H goes on one side, OH on the other side, and that splits. So do you see that it was a big molecule with two rings? And then on the product side, it's two single rings? Okay, so that is hydrolysis. Remember, think of hydrolysis as breaking with water. I'm not breaking a double bond, though. I'm breaking a single bond by adding water to the molecule. What about the bottom one? This is another hydrolysis, just another way of drawing it. So first thing you look at, you see water is a reactant, so you know it's hydration or hydrolysis. If water is a reactant, it's one of those. So then you look to see, is there a double bond being broken? Do you see a double bond broken?
No.
No, then you know it's hydrolysis. Okay? Hydration is going to break the double bond. It's going to have a double bond that becomes single. But if you see, can you see how it looks like this molecule got split in half? It basically like got split right here. OH added to one side, hydrogen added to the other side. So that's also hydrolysis. So I was just trying to do different examples, different ways of drawing them, just to get you to see that's what you're looking for. Hydrolysis, water is a reactant, and I'm taking a bigger molecule and making two smaller molecules. But you can also remember it's hydrolysis if there's no double bond and water is a reactant. That'd be another way to remember it, okay? Because if there's a double bond in water, then you know it's hydration, okay? So hydrolysis is if there's water and no double bond being broken, then you know it's going to be hydrolysis. This is digestion. All the breakdown reactions use hydrolysis. Splitting big things into smaller and smaller pieces. Okay, what about that?
Okay, so this one is hydration.
Yes. Okay,
Okay.
right? So do you see that water is a reactant, breaking the double bond, adding that water to it? What about the next one? Hydrogenation, right? Because hydrogen is a reactant. That's how you tell this one, right? Hydrogen is a reactant. See, the double bond becomes a single bond. So it started off with the double bond and now it just is a single bond. It doesn't change otherwise. It's just that bond that changes. This is hydrogenation. Hydrogen is a reactant. And that double bond becomes a single bond. The way to tell hydrogenation.
So would this last one be hydrolysis?
It's not hydrolysis because remember hydrolysis, water is a reactant.
Yeah, but I don't see no reactant.
Where's water? No, you remember everything on the left is reactant, everything on the right is product, right? So if I don't see water on the left, then I know it can't be hydration or
It's condensation.
it's condensation.
Oh, whatever, girl.
Yep, it's it. As long as you pick it out, you can remember it as it's the condensation.
Condensation.
Yeah, like what happens when your windows steam up, condensation. Okay, so in this one, the way you can remember this is water is a product. Okay, so that's going to make this different than the other ones. And do you see that I'm taking this molecule and like linking them together? I'm pulling one of the H's and this OH, and I'm using that to form water, and that leaves the link between them. So you see that the nitrogen and the carbon, that they end up joining together. So this one and this one end up being linked together in one long chain. So that's what condensation does. Condensation is what you do when you like build muscle, when you build proteins, when you have to link things together. You pull a hydrogen off of one molecule, an alcohol or an OH off of the other molecule, and then that forces them to link together to stay stable. Remember, because they always have to have a certain number of bonds. So if I pull a bond off, that's going to leave that bond empty. So it needs to form that link to be able to remain stable. So that's condensation. Water is a product. Two smaller molecules become one. So they join together. Okay, so here is this, and this, I feel that this will, hold on, that this really like summarizes everything that happens in chapter 5. It's just about, other than the lipid stuff, this summarizes all of the different kinds of reactions and an example to be able to identify. So remember that these are the first 4. synthesis, decomposition, single and double displacement, like recognizing them just from a chemical reaction. Combustion, we talked about regular complete combustion, and then we also talked about incomplete. Then we talked about recognizing oxidation and reduction. So oxidation being loss of electrons, loss of hydrogen, or gain of oxygen. Reduction being gain of electrons, gain of hydrogen, or loss of oxygen. So we went through examples with that one. We just talked about or went through some examples of hydrolysis and condensation. We also just went through some examples of hydrogenation and hydration. So I will give you this on the exam. So you will have this chart, okay? So next time I'll have some handouts so that you can have it. Like it's just a small little piece of paper. So this way, you don't have to worry about writing all these ones down, but you do need to make sure you go back and practice identifying them, okay? Practice identifying synthesis versus decomposition, single versus double displacement. What is combustion? What is incomplete combustion? Really, the only thing in chapter 5 that's not like really summarized here is the information about lipids. So what is a fat? What is an oil? How are they different from each other? Because we talked about like plant sources versus animal sources. And so that material, that information isn't really on here, but you should know those differences. Remember I told you you don't have to draw anything, right? But you should be able to look at a fatty acid chain and tell me if it's a saturated, monounsaturated, or polyunsaturated, depending on if it has no double bonds, one double bond, or two or more. You should be able to tell me which one those are. And then you should be able to tell me that saturated are those that are solid at room temperature because they can pack in tight. Unsaturated are going to end up being liquid at room temperature. So I'll just put down here lipid info. And I think one of the last things one of the things we also talked about is like, why do you need fats and oils in your diet? What do you use them for? Why does the body need them? Right? So that was like a slide all on its own. Okay? So I'll have that for you. Practice those ones. My suggestion, go back through and look at the slides. See if you can pick out, like remember there's some balancing equation slides on there. So see if you can go through and pick them out. Remember that the blank PowerPoints are posted in Moodle. The ones with notes on them are also posted in Moodle. So those are really good ways to try and practice to see if you know it. Because if you can answer it in the blank and you check your answer in the marked up PowerPoints or in your notes, then that way you'll be able to check and see if you've got it. All right, so then that takes us into 6, not that, 6. So 6 is the second nutrient. So we have talked about lipids now. We've talked about fats and oils. And so now we're talking about carbohydrates. So the term carbohydrate is exactly what it is. Carbo, you think of, go ahead.
So Wednesday, the day I missed, y'all talked about.
We did all of this. Yeah, chapter 5 stuff. We did oxidation, most of chapter 5. We did oxidation reduction, and then we did all of the different types of organic reactions. Yeah, that was last time. And lipids was in that too. But remember, that lecture is posted. So if you can go back and go into Moodle, go to exam 3 material, you can like listen and watch and take notes on that so that you it'll help you practice too. Okay. So the term carbohydrate really means carbon and water. Carbo is like carbon, hydrate, think of water. And in fact, the ratio of carbons to hydrogens to oxygens is really like for every carbon, there's a water molecule. So it's like CH2O. So we are going to talk tonight about what they call simple sugars. Okay, the simple sugars are the little sugars. They are made of just a single sugar unit or 2 sugar units. They don't require very much digestion. They get absorbed pretty easily. On Wednesday night, we will talk about the polysaccharides, the really large carbohydrates, and maybe we'll get a chance to talk about blood groups because those are the mediums, those are the in-between size ones. So first off, when you think mono means what? One. And the term saccharide means sugar. So monosaccharides just mean a single sugar. Monosaccharides, these are the smallest of the carbohydrates. They typically contain 6 or fewer carbons And remember, every carbon like has a water. So for every carbon, there's 2 hydrogens and 1 oxygen. Disaccharides, the term di, you think 2. So that means 2 sugars. So it's really where 2 monosaccharides are joined together through a condensation reaction. And you have to break them down or digest them in order to absorb those simple sugars. So those are things like sucrose, table sugar, maltose, and then lactose, that milk sugar we talked about in chapter 5 as well. So we're not going to do too much with the oligosaccharides. We might get a chance to talk about blood group typing, depends on how things go. But those are kind of like the in-between sugar groups where more than 2 but less than 10. But we are going to talk about polysaccharides. Poly, I always think of many. Okay, so like a polymer is a lot of things linked together. So polysaccharides have lots of sugars. We're not talking about like 10. Most polysaccharides have hundreds or thousands of sugars. So they are huge. In comparison to mono and disaccharides, polysaccharides are like thousands of times larger than a single sugar unit is. So we'll talk about like starch. So starch is what you find in flour. Any kind of grain that gets ground up, whether it's flour, rice, oats, potatoes, they all have starch. So this just sort of shows you like a little schematic about 1 versus 2 versus lots and lots of them. So we're going to start with the mono. We're going to start with the singles. So this is glucose. Okay, so glucose is the most abundant of all the monosaccharides. Glucose is also known as blood sugar. In this, you find that monosaccharides are named according to the number of carbons and where their double bond oxygen group is. And so this one, do you see that that double bond oxygen group is on the very end? So the one where it's a C double bond O with an H on the end, that is called an aldehyde. Do you remember that as a functional group? Aldehydes are always on the end. It's when you have that double bond oxygen and just a hydrogen on the end. The number of carbons, there's 6 of them in glucose, so they call it a hexose. The OSE at the end. Hex tells you there's 6 carbons. The term OSE tells you that it's a sugar. Okay, that it's a carbohydrate type is probably a better way to call it. Because there's like, one's like,
The one with the 6 on it?
so see the 6 carbons in the chain, that's why they call it hex. Because the term hex is 6. And the OSE on the end tells you that it's a carbohydrate. Do you notice that all those middle carbons have alcohol groups? Carbon 2, 3, 4, 5, 6, all of them have an OH. They all have an alcohol group. That's what makes them polar. So even though this is a pretty big molecule, the fact that every carbon has an alcohol means that those bonds are not shared equally. This molecule has an overall charged, slight charged nature to it. This is why it mixes with water. So sugars can mix with water because of all those alcohols. They sometimes say it's a polyalcohol, which just means it's got a lot of alcohols. So having that polyalcohol characteristic improves its polarity and helps it to dissolve in water. So lots of alcohols increases polarity and makes it soluble in water. So this is why all those little sugars, right? Sucrose, table sugar, fructose, like in honey. So if you take a spoonful of honey, you put it in your tea, stir it up, completely dissolves. Blood sugar, dissolved in your blood. So that's glucose. So not only can we have aldehydes, there can also be a ketone as part of the chain. So it really just depends on where the double bond oxygen is located. If the double bond oxygen is on the end, it's always an aldehyde. If the double bond oxygen is on the second carbon, which means it's inside of the chain, then that's going to make it a ketone. So you see the difference between those. So benzaldehyde, formaldehyde, those have their double bond oxygen on an end. Whereas notice like pyruvate and butadiene, that's like artificial butter flavor that they like to put in margarine. I can't believe it's not butter flavoring. That's what that chemical is. And it fools your taste buds into thinking it's butter, because that's the chemical that your taste buds associate with things that have butter flavoring. So you can buy artificial butter flavoring for things or food, and that's that chemical that they put in it. But ketones, notice the double bond oxygen's in the middle versus on the end. Now you will also get, when you take your exam, because we started using these last time, remember that these are the functional groups. So you will have those to use as well. The functional groups. Please don't take them home. If you have multiple ones at home, I'm short a few. I had to make some photocopies. For the last exam. I think people have like meandered out with them because I've only got like 30 and I have 34 students in my day class. So I was like, I've run out. I make copies. But it's either going to be on the carbon at the top of the chain or the second carbon. If it's on the end, it's an aldehyde. If it's on the second carbon, it's a ketone. And so notice where it is. In this first one, notice the double bond oxygen's on the end. So that's an aldehyde. Count how many carbons in the chain. So there's 6. So they will call this an aldohexose. Right? So 6 carbons makes it a hexose as part of a sugar. And the aldehyde on the end is an aldo. So look at that one on the right, though. That one, instead of an aldehyde, this is find the double bond oxygen.
Where you at?
So the one on the right, find the double bond oxygen. It's not on carbon 1, it's on carbon number 2, the second one from the top. So that makes this a keto instead of because it's a ketone, so they just use the first part. How long is this carbon chain? So that makes this a pentose. So remember, pent is 5. So they name sugars based on how many carbons in the position of that double bond oxygen. So I can have an aldopentose. That would be 5 carbons with the aldehyde on the end. I could have a ketohexose, which would be a 6 carbon chain, double bond oxygen on the second carbon. They said up here, if you had a 4 carbon group, it'd be a tetrose. We really don't do that very much. Really only pentoses and hexoses are the common ones. So it's either going to be 5 carbons or 6 carbons. Those are the more common sugars that you're going to see or have to deal with. An aldo means there's an aldehyde on the end. A keto means there's a double bond oxygen on the second carbon, because it's always either going to be on the first carbon in the chain or the second, always.
So you said the longest chain on this side is 6, because we ain't gonna include that.
The O is not a carbon, it's an oxygen, right? So if you just count carbons, 1, 2, 3, 4, 5, 6, that's in the aldehyde, the double bond oxygen's on the end, so that's why they call that an aldohexose. But the one on the right, if you count the number of carbons, you only see 5. So that double bond oxygen's on carbon number 2, that's why it's a ketopentose. So the last part that you're like going to go, sugars have chiral carbons. Do you remember what chiral carbons are? What is a chiral carbon? It's a carbon that has how many bonds? What's the rule? A chiral carbon always has 4 single bonds, and all the groups are different, right? So remember that one group would be an H, one an OH, one could be a CH3, the other one a Cl. That's a chiral carbon. Remember, all the groups above, below, left, and right have to be different. Okay? So when we look at this is glucose. Do you see that carbon 1 is not chiral? Why? The carbon at the very top, why is it not chiral? Because it has a double bond. Remember, it's got to have 4 single bonds. So you remember I told you cross off any with double bonds, can't be chiral. Okay? They also crossed off carbon number 6. Why? Find carbon number 6. See how it's got an X through it? Why? Because it has 2 hydrogens. They have to have 4 different groups. So remember that this has a double bond. And that's not chiral. This has 2 hydrogens directly connected to it. It's not chiral. But look at the rest of them. So looking at carbon number 2, on the left I have a hydrogen, on the right I have an alcohol, an OH. Above is a aldehyde group, and below is this whole part. Are those all different? The group above, the group to the left and the right, and the group below, are they all different? Yeah. Do you see this purple? Everything, remember, it's everything below, not just what's next to it, right? So it's everything above, below, left, and right. So can you see that those are all different? The way I circled them, I circled the purple and carbon number 2. So that has that little asterisk. This is a chiral carbon. So remember, I can do a mirror image and they're not superimposable. Carbon number 3 is chiral. Carbon number 4 is chiral. Carbon number 5 is chiral. Geez. So all of those can exist as mirror images. So I can flip them, and that mirror image is not going to be superimposable. So that means that there's lots of different ways that sugars can have their hydrogens and alcohol groups connected or arranged in this chain to create molecules that look almost identical, but they're not actually mirror images. So here's some examples. Or not that one, this one. So there's glucose. Glucose on the left. Look at the one in the middle. The one in the middle is galactose. Do you remember that galactose is one of the parts of lactose? So remember when we were talking about people that have lactose intolerance? I said you have lactose and it gets broken into glucose and galactose. So looking at that, is carbon number 1 identical? With glucose and galactose is the first one at the top. Those are identical, right? They're both aldehydes. Carbon 2, is it identical? 3? 4? No. How about 5? And 6? The only difference between glucose and galactose is the position of a hydrogen and an alcohol on carbon number 4. So here, come on. Here and here. Do you see that those are different? Glucose is blood sugar. If galactose is absorbed, it gets converted to glucose. So your body recognizes glucose as that blood sugar. And even though there's only that difference, that's enough of a difference that enzymes actually will take galactose and convert it to glucose for your cells to use for energy. It's like that specific. So remember, those enzymes can be very specific in what they can manage. So you notice the D. See, it's D-glucose, D-galactose, D-talose is another one. The D is the way that they recognized right and left-handed forms. So remember, I told you that if you have a chiral carbon, you end up with like a right and left-handed version. So in this, here is D-glucose. Well, here's its mirror image. Can you see that? So if you look at the D, the one in the middle, see carbon number 2 has an alcohol group on the right. Carbon 3 has an alcohol group on the left. Carbon 4, carbon 5 have that OH on the right. But if I look at the one next to it, do you see that these look like mirror images? that they're flipped? Carbon 2, the alcohol group is on the left, not the right. Carbon number 3, the alcohol group's on the right, not the left. Do you see how they're like flipped? So if you thought of it as being like a mirror, those two look identical. So they said, okay, well, that's the left-handed form and that's the right-handed form, basically. They said these are the mirror images. So they came out with a way of identifying left and right. They used D and L. In nature, almost all carbohydrates exist in the D form, which is kind of interesting. Like almost all sugars in nature are D sugar types. But almost all amino acids, which are used to build proteins, they're all L because they have chiral carbons too. Just sort of odd. Don't really know why, but it just occurred that way. So when you find glucose in nature, glucose exists as D-glucose. This is the only structure that I expect you to be able to identify. So this, either written this way or written this way, this is D-glucose. It is blood sugar, and so that's really the reason for you to recognize it. So looking at D-glucose, it's a aldohexose. Each of these little center pieces, those are carbons. It's sort of a semi-skeletal structure that they do with it. So do you see 1, 2, 3, 4, 5, 6 carbons in a row? The top carbon is an aldehyde. And then the position, the way I remember to recognize D-glucose is I remember right, left, right, right. Because that is the positions of the alcohol on carbons 2, 3, 4, and 5. And that's the position of the alcohols on carbon 2 through carbon number 5. So if I had this drawn, because I'm not going to ask you to draw it. If I had it drawn, then I would ask you, which one of these is D-glucose? So you'd be looking for aldehyde on the end, and then counting down the carbons, carbon 2, alcohol groups on the right, carbon 3, the alcohol group's on the left, but then 4 and 5, the alcohol group is on the right. And 6 is not chiral, so it's just written as CH2OH, right? Because it's got 2 hydrogens, so they don't even try to like write it out how it is spatially. It doesn't matter because it's not going to be a chiral carbon. Just those middle 4 are. Yep, C2 to C5. C2 on alcohols on the right, C3 alcohols on the left, C4 and 5 alcohol groups are on the right. So right, left, right, right. That's how I remember their position when I look for the molecule to match it. Okay, so we're going to talk about the most important, the most abundant monosaccharide that's found in nature is called glucose. Okay, you also know it as blood sugar. You've probably heard of it called dextrose as well. Sometimes they call it grape sugar. It's found in fruits, vegetables, corn syrup is a good example, but glucose, remember, is also part of disaccharides. So like sucrose is glucose and fructose. Maltose is glucose and glucose linked together, and lactose is glucose and galactose. So glucose makes up a lot of disaccharide components. In fact, glucose is the sugar that makes up starch. So starch can be 5,000 glucose molecules all linked together. So that's really why glucose is so abundant, because it's found in so many different carbohydrates. In the body, they talk about your blood sugar. Blood sugar, and we did the banana lab last week, so if you were in lab, we did the little glucose dipstick test. And so remember, it was the little yellow pad and it turned green based on how much sugar was there. And remember that was milliliters per deciliter of liquid. So you had milligrams per deciliter of fluid. So that's where that unit is. Most people don't talk about the units. They say, your blood sugar is 100. That's good, right? They don't usually tell you what the units are, but it actually is, if your blood sugar was 100, it's 100 milligrams of glucose per deciliter of blood. So it's talking about how much sugar in a certain known volume of blood that has. It is considered a normal range to have blood sugar between 60 and 110, okay? Anywhere in that range, you can be 60, 62, 70, 80, 90. You can be all the way up to 110, and that's considered normal blood sugar. Glucose has always been called the preferred nutrient energy source. So it's the preferred nutrient energy source for cells. And it is because your cells can use enzymes to do combustion. So remember, combustion is taking fuels, breaking them down, generating or using oxygen to generate carbon dioxide and water. So we can take C6H12O6, that's glucose, 6 carbon sugar. If we react oxygen with it, we can make carbon dioxide and water and lots of ATP. Remember, ATP is that universal energy molecule for the cell. You saw it on the T's? I hope you got it right. All right. So all you need to do this is sugar and oxygen. Where do you get sugar? From your diet. Where do you get oxygen? All you have to do is inhale, right? So your cells, it's not hard for your cells to get the reactants. And then look at the products. Carbon dioxide, how do you get rid of that? Right? When you exhale. So carbon dioxide, you can get rid of it just through the lungs. And then water, well, water is in there anyways. Water's already in the cell. So it doesn't make any kind of waste molecules. Your kidneys don't have to do anything because we have sugar plus oxygen making carbon dioxide and water. So your lungs bring in oxygen, get rid of carbon dioxide, and the water just becomes part of your cell fluid. So this is why your body, your cells, would really like to run off of glucose. It's very, very convenient because you get a lot of energy and it's easy to get the reactants and it's easy to get rid of the products. The problem is if you ingest too much, okay, when you go above 110, so greater than 110 milligrams of glucose per deciliter of blood, that is called what? What is it if it's too much?
Stroke.
No, I mean, those are all problems you can run into, but what is that term? If your blood sugar is higher than it should be, hyper, what? Not tension, that's blood pressure. Glycemia. So this is hyperglycemia. Okay, so glycemia is referring to blood sugar. Hyperglycemia means blood sugar over 110. This happens routinely with somebody that's a diabetic. So if a diabetic eats any kind of carbohydrate, and this could be simple sugars, it could be monodisaccharides, it could even be starches, because once those sugars get absorbed into the bloodstream, if the diabetic doesn't have insulin, then sugar stays in the blood. It doesn't go into the cells. So I told you that your cells want to run off of sugar. That's optimal because it's really easy. But if you don't have insulin, then there is no way for the cell to get glucose into the blood. And that creates that aspect of diabetes mellitus. So it is estimated that in the United States alone, there's about 110 million people that have diabetes. Okay? So in terms of healthcare with your patients, you are going to take care of diabetics. You are going to take care of people that have heart disease. Okay? And sometimes both. Diabetes can lead to infections and amputations. Diabetes can lead to blindness. Diabetes can lead to kidney failure, which then requires that patient has dialysis. So we have all of these like side chronic health issues that build up, and it's billions of dollars a year spent on trying to treat diabetes. So understanding what it is when you're trying to help your patients is really important so that you can explain like the whys behind what you need to make sure you do, why you need to be careful about something, or like everything from like you get a cut to why you should maybe not have the donut. Okay, that's like one of the hardest things to get across to people, but sometimes trying to explain that. So there's really two types. There's type 1 and type 2. Type 1, they commonly used to call juvenile diabetes, or they call it insulin-dependent diabetes. So what happens in what forms type 1 diabetes mellitus is because there's something that damages the pancreas. It might have been a virus. You might have not been born with functional cells that make insulin, but for some reason, your pancreas doesn't make insulin. Okay, so this is like the critical part, is there's no insulin secreted. So remember I told you when your blood sugar goes up, your pancreas has to secrete insulin to allow your cells to allow glucose to go in. Without insulin, the body cells have no idea that there's sugar in the blood. So you eat like a sandwich, the bread gets digested, sugar in the blood. You don't have insulin, that sugar just stays in the blood. So then later you're like, well, I'm kind of hungry, let me have a candy bar. Okay, more sugar going into the blood. Then you eat some more carbohydrates, more sugar in the blood. And so what happens is your blood sugar goes higher and higher and higher. As blood sugar increases, normally your pancreas would secrete insulin and bring it back down into the normal range. But if you're a type 1 diabetic, your pancreas doesn't work. And so without that, now you go into this state of hyperglycemia. So not for like 10 minutes or half an hour, you're in hyperglycemia for hours, even days. When you're in hyperglycemia, that sends a message to your body cells, we're starving. Even though there's tons of sugar, even though your blood is sweet like molasses, okay? So lots of sugar in the blood. Without insulin, the body cells have no idea. So the body cells stay closed. They cannot open and allow glucose to go in. So they go, okay, well, we're starving. So we're going to have to burn fat, and we're going to have to start breaking down proteins because those are the other two nutrients, right? So we have lipids, which is fats and oils. Then we've got carbohydrates, then we got proteins. Those are your three nutrients. So if we can't use glucose, we have to burn fats and proteins. When you burn protein, where do you get protein from? You can get it in your diet, but if there's not enough glucose, you're going to have to use body proteins. And most of your body proteins are in your what? Your muscles. So you start to see the person starts to have muscle wasting. It is because the body is like basically digesting its muscle in order to send those proteins to the body cells to use for energy. When you burn fat, so you notice that this person, a lot of times this person is always hungry. They're always thirsty because their blood sugar is so thick, they think they're dehydrated. So they're like, I'm really thirsty. So they're always drinking stuff, always eating. But instead of gaining weight, they're losing weight because they're burning all the fat that they can't store because their body thinks they're starving. And they're also starting to break down protein. So you might see that they look like they're starting to shrink. Like they're actually getting smaller and smaller and smaller, even though they're eating constantly. The breakdown of fat and protein, when it's balanced, your kidneys can handle it. When it's in this extreme combined with hyperglycemia, then you can go into a stage which they call ketoacidosis. So DKA, which is diabetic ketoacidosis. That's the kind of term. When you have patients that are in DKA, that is diabetic ketoacidosis, that is when their blood has got so much acid in it that it actually causes the pH of the blood to begin to drop. This is all because of breakdown of protein and fat, trying to use protein and fat as the primary nutrient source, but also having hyperglycemia on top of it. So you know people that do the keto diet? I don't know if you know anybody who does any of that, right? These are people that they eat meat, okay? They eat meat and salad. Some people don't even do that. They eat like vegetables, they eat meat, they eat salad. They don't eat anything with starches. So they don't eat potatoes, they don't eat rice, they don't eat breads, they don't eat anything that's sugary. They strictly eat protein, and they even eat like avocados. So they eat like a lot of fat too, but they try to stick to the healthy fat. Most people do. Okay. The difference is they don't have hyperglycemia, right? They're not eating any carbohydrates. So whereas somebody that's a diabetic, their blood sugar is really high and they have this high acid level, and the two of those combined kind of overwhelms everything. Somebody that's on following a strict keto diet, they don't have hyperglycemia because they don't eat carbs. So if they don't eat carbs, there's not going to be any hyperglycemia because there's no sugar. They don't eat sugar, they don't eat bread, they don't eat anything with flour. So this would be a keto diet would be wonderful for a diabetic, because a keto diet would keep glucose low and stable. So in that, but you can't just eat just like fat and meat though, because I know some people that are like, but I don't like vegetables. Because if you eat nothing but fat and meat, there's no fiber and you'll become so constipated it's not funny. Okay? That's why you got to have salads and vegetables. You got to have some greens. You got to have the spinach. You've got to do, other things to try and make sure that you're like moving things through regularly so you don't get so bound up. Okay. The problem with somebody that has DKA, a diabetic that has high blood sugar, that has high acid levels because they're not breaking down sugar, they're breaking down proteins and fats, they get very tired, lethargic, they can actually lose consciousness, they can actually go into a coma, and if it's not reversed, it can kill them. So type 1 diabetes can be life-threatening if it is not managed. Most of the time, these people are brought into the hospital because of these symptoms. Sometimes people think they find them like they think they're drunk or something because they're so out of it, because that high acid levels are like, they're combative. They're like not going to reason. I'm fine. Everything's great. And they may even be kind of slurry. So people are like, what kind of drugs are you on? And then they bring them in. What is the highest blood sugar you've ever seen? 900. Should be between 60 and 110. So 900 is 9 times more sugar in the blood than should be there. Huh? And she couldn't see. That's why I said blindness.
It'll be the family.
Yeah, the enablers.
Yeah.
So what you have to do for a type 1 diabetic, you have to give them insulin. You can't like, oh, well, we'll just stop feeding them carbs and they'll be fine. You have to start them off. You've got to bring their blood sugar back into that 60 to 110 range. If they have had like hyperglycemia for a while, sometimes bringing them back into that 60 to 110 range, they feel terrible. They get really shaky. It's almost like their blood sugar is so low because they've had it high for so long. So sometimes you actually have to like almost like step them down, go from 900 to 600, and then try to go from 600 to 500 and like bring that blood sugar down slowly, may even be over like weeks before you can get them down into, and like some, if you can get them into the 100, you're happy. Okay. Because any lower than that and they can't handle it. Like they feel like really anxious and jittery and can't think. It's like they're hypoglycemic. It's like their blood sugar is so low because they're so used to it. So you give them insulin, brings their blood sugar down, and then they have to monitor their blood sugar. So they have to check, they have to do finger pricks. There's now like the automatic monitoring. And so I know you've probably seen people that have like a little piece that's like taped onto their arm. Most of the time it's their arm. It can be other parts of the body, but it's really common to see them here. And so they can like take their phone and literally like sample. It's all done Bluetooth now so that they can check their blood sugar constantly throughout the day, which is really helpful for some of the type 1 diabetics that have big swings. Some diabetics eat and their blood sugar goes up to 300 just from eating. Like it's really fast. And then when they take insulin, their blood sugar crashes. So they have to be very careful about how much they eat, what they eat, and how much insulin they take. Without proper management, hyperglycemia really ends up causing problems. Hyperglycemia, I said, is like thick blood. So think about like water versus maple syrup. right? So if you're going to squeeze water out of your water bottle, does it just fall out? Yes. But if you're trying to get syrup out of the bottle,
I take a squeeze.
right, it requires force and effort. That is what your heart has to do. So your heart is used to trying to pump water. Now your heart has to pump syrup. So can you see why, like, your heart has to push extra hard to get the blood to move? That leads to heart disease. Thick blood does not flow well, so it ends up going into capillaries and like slowing down. Capillaries are the very, very smallest blood vessels. So though if it slows down enough, those capillary beds will just shut off. So this is what happens when people develop what they call neuropathy. That is because the blood flow to the nerves has gone down to the point that you can't feel anything anymore. So people say the bottom of their feet's numb. Their fingertips, I can't feel my fingertips. Well, that means they're at risk of cutting themselves and not even knowing. So one of our friends, a type 1 diabetic, he had a cut on his foot because his toenail, like one toenail was too sharp. It cut the inside of his toe. He didn't even know because he couldn't feel it. And so then when he he was like inspecting his foot, and his like toe was huge because it had gotten cut, and there's not good blood flow, so it doesn't heal. So that cut persists, just stays there and stays there and stays there. And the longer an open wound is there, the greater the risk of infection. So that's what happens with people get an injury, a cut on their extremities, and then they end up having amputations because it doesn't heal. That thick blood can damage capillary beds in the back of the eye. So they can actually damage the retina, the blood supply to the retina. And so blindness can result because of prolonged hyperglycemia. Also the little filters, the small little filters that you have in the kidneys. So the job of your kidneys is to filter out fluid waste. There is so much sugar in the blood, the kidney actually ends up excreting some sugar. Oftentimes they'll have sugar in their urine. Sugar in your urine increases your risk of developing all kinds of infections in and around the urethra. That is like one of the worst things that I've ever seen in my life. Okay? But it can also cause those filters in the kidneys to be damaged and convert to scar tissue. So more than half of your patients that have to go for dialysis, they're diabetics. So that hyperglycemia causes this like kind of chronic issue. You're at increased risk of heart disease, increased risk of heart attack, increased risk of stroke, increased risk of kidney failure, increased risk of blindness, neuropathy. All of those are really because of that hyperglycemia and that poor management in terms of diet. Okay, I will quit there and we will talk about type 2 on Wednesday and then finish up this chapter.